All right, good morning everyone. My name is Jimmy Torre. I'm here to present at LambdaConf 2017 as a second-time speaker, third-time volunteer, on my own personal research project, which is Pervasively Reconfigurable Computing, PRC. And if you want to contact me, my email address is at the bottom. And if any of you are amateur radio operators, catch me at KC9YYY. So, I'm going to go through my title in reverse, Pervasively Reconfigurable Computing. The goal of this project is to collapse the abstraction stack between physical and logical semantics. What do I mean by physical and logical semantics? Logical semantics is perhaps easier to understand. It's what we usually think about when we're programming, or when we have AND gates or OR gates, when we manipulate discrete digital elements so as to encode information. But we also have physical semantics, because all of our computers are actually physical devices, and so there are continuous phenomena or phenomena which are not entirely captured by discrete mathematics, which then we discretize by taking certain regular intervals, certain regular repeatable phenomena, like voltage pressure, or the presence or absence of billiard balls, or the presence or absence of waves in a pool of water. And then declaring that above a certain threshold, this represents one particular discrete signal. Below a certain threshold, this represents another particular discrete signal. And what is especially entrancing to me about a transistor is that it is so very close to physics. It's just a semiconductor. It's just a dielectric effect. But with a single transistor, you can in fact produce general purpose computation. We have at the bottom left the single transistor NOR gate. So that is a PNP resistor, I believe, and with a single transistor and 3 resistors, and resistors are just wire of various lengths, you can produce a NOR gate, and a NOR gate is sufficient for universal computation. And everyone knows what a NOR gate is. If you don't, raise your hand. Good, excellent. But there are other kinds of logical semantics which would be interesting to see if we could bring them down closer to the level of physics, as opposed to operating at a high level of abstraction where we might simulate them. And particular interest to me are reversible logic, asynchronous logic, and reconfigurability. So, reversible logic is a bijective mapping, as opposed to classical Boolean logic, which is a one-way mapping from inputs to outputs. The particular benefit of reversible logic is that, being a relation, if the inputs are or if the outputs are passed back to the inputs, then the original state is retained, or rather is resumed. So we have here the transition diagram for a Fredkin gate, and a Fredkin gate has 3 inputs and 3 outputs. So with reversible logic, you must, if you're parity preserving reversible logic, you have the same number of input terminals as you have output terminals. And we see that the Fredkin gate actually doesn't appear to do very much. It seems to just map A to A prime, B to B prime, and C to C prime, with the exception of the second and third to last, where depending on the value of, or rather with the value of A being set to 1, we have B and C swapping with each other. So the Fredkin gate can also be described as a controlled swap. And we can see pretty easily that if we pass 101 in through ABC, we get 110. Pass 110, we get 101. So the Fredkin gate, along with Toffoli gates and a whole bunch of other reversible logic gates, are again single gates, which are also sufficient for universal computation, which I will not prove today. So that's the cool thing logic-wise. Physics-wise, it was shown by Landauer that if one wishes to have physically reversible computing, one must first have logically reversible computing, because for every irreversible operation, say take every irreversible bit operation, so say take an AND gate. In an AND gate, if you have 2 high signals, you produce a high at the output, but if you have only 1 high signal on one of your 2 inputs, and your other input is low, then you must somehow dissipate that 1 unit of charge, because your output will also be low. So the absolute lower bound for how much energy that must be dissipated so as to discard that information, so as to erase that information, is k times t times the natural log of b. B is your number of bits, T is the temperature of your circuit, and K is Boltzmann's constant, which is the average kinetic energy of, it is related to the average kinetic energy of particles interacting with each other. And why is this an issue? Well, as we've progressed through minimization, going from meter-sized computer elements to micrometer-sized computer elements to nanometer-sized computer elements, energy dissipation has become the dominating factor in terms of the ability to continue the minimization process, but also in terms of the ability to produce accurate results. Because as we're getting to the point of diminishing returns, where if we minimize our process size any further, then the errors which accumulate either through the process or through the operation of the machine itself begin to destroy a greater number of our miniaturized transistors than we actually have been able to put onto the chip with a smaller process size. So, if we are to continue the process of miniaturization and continue the process of increasing clock speeds, then at some point we're going to have to either change our material science or change our logic. And reversible logic is one such proposal. Asynchronous logic, and I'll explain why I'm interested in reversible and asynchronous and reconfigurable in just a moment. But asynchronous logic is similar to reversible logic, also has energetic advantages. There is no clock signal. Instead, there's synchronization that must occur between each individual component of a hardware circuit, as opposed to a classical hardware circuit where you have a clock signal that actually primes each gate for the next unit of voltage pressure, which represents a digital logic symbol. And we have an example here of a Mueller C gate. So the Mueller C gate is again a variety of, well, actually it's a variety of OR gate, but in the absence of two identical input elements, it simply returns the previous element that was on its output. So we see here that we have something which seems kind of like, or rather, which seemed to me kind of like in this resonant with reversible logic, because we have an interaction, not necessarily dependency, but an interaction with our outputs and our inputs. But we're lacking the parity preserving of reversible logic, which means that even though we might have a benefit of losing the clock signal, we still have to dissipate input somehow. So with a reversible and asynchronous fundamental hardware element, then we'd be able to receive the maximum advantage, or our maximum advantage in terms of energy conservation, which again is the ultimate upper limit, the ultimate restricting reagent in terms of our computational throughput. So, this work? Yes.
Out of curiosity,
Yes, please ask questions.
if you use reversible logic, so the upside is that you don't have to dissipate, you reverse because you're not losing any bits. But what's the downside? Your programs become huge.
So yes, we can see here that to have what looks like only one bit of control, we actually have 8 inputs and outputs. You do have the issue of waste and auxiliary bits. So either you have auxiliary bits in the beginning to set up your right control constants, and you might have waste bits in the end because you don't really care about.
So you still have to allocate your bits up front.
Yes, and you have a notion of. So it's kind of like if you have explicit side effects. This is kind of like having explicit. Well, actually, I'll get to that later. Never mind. That's separate. This is permutation. All of your computation must be represented as permutations upon whatever initial set of bits that you have. Yes?
Aren't you just sort of deferring the dissipation of that energy? Because at the end of your computation, you're going to output a number or something. You just have to dissipate all that information.
Correct. So that is correct insofar as your final output will only observe a certain subset, perhaps, of your hardware circuit, but I/O is troublesome for many reasons like that. So then you've now successfully segregated all of your energy management to when you input and when you output. Yes. So there's actually a notion of reversible logic has a lot of applications to quantum computers because unitary quantum evolution is a reversible process. It's just actually the mathematics behind it is braid theory, which I don't know too much about. But if you think of a set of spaghetti and you want to turn the set of spaghetti into a set of straight lines as opposed to tangled spaghetti, then if you set up the tangled spaghetti correctly, then the process of unraveling it to produce straight line spaghetti represents your actual computation you so desire. Then all you've done is a permutation. You've still had continuous links from one end of a path to the other end of a path. But you're correct that you're both correct that you will likely have to ignore and let some end bits be captured and recycled some other way. Because the key is that there's a very close correspondence between the physical phenomena which embody symbolic phenomena, and then this also goes in reverse. If you have a particular set of symbolic phenomena you'd like to represent, you might require different physical phenomena. All right. So, the digital logic element, which I propose, I call a universal cell insofar as it is based off of two research projects, one out of MIT called Reversible Asynchronous Logic Automata. They also called their single universal reconfigurable units cells, and off of Kenichi Morita's Reversible Logic Elements with Memory. We can consider a universal cell to be a reversible logic element with memory that also can be reconfigured. That's been extended with reconfigurability. So a UC is reversible and parity conserving, so it doesn't throw away any bits. It's always a complete bijection from input to output. It is asynchronous in that there is no clock signal, and particularly it is pool-based asynchronous, which we'll get to in a moment. But you have two different kinds of asynchrony. Either you can prompt the synchronization signal, the synchronization between two units which are going to communicate, by having the upstream unit signal first and say, I have data which I wish to transfer, are you prepared? Or you can have the downstream unit simply draw from the upstream reservoir at its leisure, as fast as it can go on its own heartbeat. And it is reprogrammable. So RLEMs, reversible logic elements of memory, are reversible and asynchronous by default, but this is an extended RLEM with reprogrammability. And this automaton then supports the three major functions which you need to have a single hardware element, like a transistor, which can perform all of your computation. It must be able to at least discriminate in a binary fashion, so that you can have some nonlinearity. Otherwise, you just have a block of undifferentiated crystalline structure. It must be able to store and persist its decision. And critically, it must actually be able to move the physical carriers of digital logic through space. Because this is not a Platonic world, we have actual constraints of die size and dimensionality. So if we compare RLEMs, which we have, or UCs based on RLEMs, which we have right here, we see that the state which is memorized is in which direction an input signal will be rotated. If the memory state is 0, it's rotated to the right. Memory state is 1, rotated to the left. And this then performs both our discrimination, so our binary switching logic. It performs our memory operation, so whichever direction you switched last, you will switch the opposite in the future. And it also then performs signal routing. So all with in one time step, you might say. The logical or the logical symbol is manipulating both its processor functionality, its memory functionality, and its wire functionality. But you don't always want to, pardon me. Oh yes, okay. And I will describe UCs more in just a moment. So then, what does formally specified mean? That's the other part, that's the first part of my title. It means that we're describing the correct operation of whatever we're talking about, in this case a universal cell, in a language amenable to rigorous inspection. So we're going to begin, and in natural language. Then we're going to continue to pseudomath, in which I have my own notation for an abstract state machine. And then we'll hopefully get to the temporal logic of actions, which is Leslie Lamport's set theory-based notation for describing the correct operation of concurrent processes. All right. Now, just a note on why I think this is interesting. If one considers the computers we have now as being universal tools, which they are insofar as they can simulate themselves and they can simulate arbitrary computation, it is somewhat unfortunate that we as operators are so very far removed from the actual nature of the physical machine. We might be able to manipulate our software to various degrees. If we have access to the source code, it's even easier. If we have powerful reflective languages, we might be able to form metaprogramming and write our own software and then inspect objects at runtime and so on and so forth. But much of the hardware and lower level elements of our computers are restricted and fundamentally restricted because they lack reconfigurability at all levels of the stack. Even if you had something like the mill CPU, where you have an exposed pipeline and you can actually do things like control when your cache gets flushed, which Intel doesn't let you do, you're still bound ultimately by whatever the original equipment manufacturer decided to lay out in silicon. And that is unacceptable to me because I'm already bound by the limitations of my skull, in that I can't go in and poke at my brain circuits directly. And if I want to learn something, I have to have a long and tedious process of absorbing it via example and repetition and multiple points of view. And so not only am I bound by physical limitations, which, as in the laws of physics, I'm also bound by what seem to be much more contingent interaction limitations. So, with PRC, with the universal cell, if at the very basemost layer of our computational stack, we create an in-principle reconfigurable device, then so long as we leave traps at every successive layer, we should always be able to backdoor ourselves, always be able to get to one layer lower in our execution hierarchy and modify it to our desires. All right, so universal cell, to give some background and due credit, is a synthesis of and this extension of two projects, the Reconfigurable Asynchronous Logic Automata by Neil Gershenfeld's lab out of MIT, and also significant contributions by David Dalrymple. Theirs was a uniform orthogonal grid. It used a token passing system where each token represented not just binary, but also not just 0 and 1, but also reconfiguration signals. And their main distinction was with stem versus gate cells. And in their stem cell state, you would have to program the next state of the cell both with how you wished your inputs and outputs to be wired. So if they had intersecting orthogonal grid, then in the stem cell state, they might produce a XOR gate with the inputs on the east and west and outputs on north and south, or northwest, southeast, so on and so forth. With reversible logic elements with memory, the interesting thing that I found with them is that they combined switching and memory operations with each time step, and they were naturally geometric because you could interpret their operation as rotation. And in particular, RLEM 3-453, which means 3 input and the 453rd described RLEM, is exactly what we saw in the previous 2 slides ago. but rendered in block format. In its left-hand rotation state, A goes to B prime, C goes to A prime, B goes to C prime, and in its right rotation state, A, B, C just map directly to their outputs. Okay, so this was described in the talk I gave last year on this topic as well, but I want to reiterate it and also make it a bit more thorough. Kenichi Morita goes through a two-stage derivation process to prove the universality of reversible logic elements with memory. The first one is he constructs a reversible Turing machine, which is completely bit-sliced. It has only one, and I'd say extremely bit-sliced. There's only a single symbol moving throughout all of its circuits that then simulates an arbitrary Turing machine that is implemented in hardware with any number of signals moving through it. But he simulates them not with three terminal RLEMs, but rather with two terminal RLEMs. Specifically, the RLEM 2-3, which we see here, which has only AB inputs and ST outputs, and it requires three RLEM 3-453 to simulate, with these particular lines drawn between, and this is a direct recreation of Kenichi Morita's diagram. Now, if we're simply concerned with the black box equivalence of two-terminal RLEMs and three-terminal RLEMs, then we don't need to consider how it is we actually draw these wires. We can say, as much as we make a relatively neat line out and around, we could also go all the way across the screen, scribble around, and come back. But if we're to have geometrically explicit logical circuits, then we must convert these wires into some number of RLEMs, which will properly convey the information from output terminal to input terminal. And that's what this grid over here is, this hexagonal grid. We have a blown up version of 6 universal cells arranged with a particular ordering, a particular mapping of inputs to outputs. So A is opposite C prime, B is opposite A prime, C is opposite B prime. And then if you combine 20-odd universal cells in this configuration, you can trace and prove out that A will in fact, or that AB and ST will in fact be matched to their appropriate input and output locations. This build order over here describes how you could go about actually tracing out the connections. So C prime of 3, which would be here, first goes to C of 3. So if we have 3 here, C prime goes to the west, and then we follow the 1s. So each of these RLEMs must be preset to memory state 0 so that they perform right-hand operations. And then it returns to the C port of 3, which matches C prime returning to the C port of RLEM 453 number 3. But these aren't actually just RLEMs. Sorry, question?
So at the beginning of each cycle, you will set up the configuration of which way each element goes and the initial data?
If they were just reversible logic elements with memory, yes, you would have to. But a universal cell has 3 different phases: wire, processor, and stem. And in the wire role, it functions as an RLEM which has had its memory frozen, so that upon switching a signal, it doesn't actually switch the memory bit. In fact, the only... so this would be... all of these are RLEMs in wire configuration. if you actually want to, which means that if we add anything more to the functionality of a universal cell, like the ability to switch from a wire state to a processor state where it can actually change its memory, then we at least have Turing completeness. We already know by this reduction that the universal cell is in fact capable of universal computation, even if at the cost of a blow-up here. But 453 is actually particularly inefficient. I like it mostly because the mapping here is regular. It doesn't make any distinction between its A, B, and C ports. But there are other RLEMs which are also suitable to simulation in this fashion with universal cells which have smaller grids. So this is like a worst case scenario for how much blow-up you'd have between RLEMs to UCs. All right. So again, the cells we have here have all been frozen into a particular wire state, which means that their memory does not change when they pass a signal either clockwise or counterclockwise, right or left. But to attain that particular wire state, they must first pass through a stem state, and it may not always be the case that you want to just pass signals across the chip. You might actually want to store some information or process information, in which case A, S, T, and B are actually processor phase universal cells, meaning that their memory has been unfrozen. So, how do you transition between wire, stem, and processor phase? So, I went back and forth between the Rala approach, where you have different kinds of reconfiguration signals for each kind of end result, that each kind of pluripotentiation or the potentiation that you want your pluripotentiable stem cells to eventually adopt, and having a single homogeneous language, just using binary logic or just using binary signals, and then increase the amount of background logic that each universal cell would have to perform so as to parse a set of reconfiguration signals. And I eventually decided on just using zeros and ones. I have some ideas about, there are some cool ideas about particle collision, where you'd have multiple tokens moving through the system, and then if two tokens both meet at a single cell, and that cell might morph into a different form. But for now, the most straightforward way is you bit bang it, you send zeros and ones to a stem cell, and then if you send it the right sequence of zeros and ones, then it will adopt processor or wire roles with memory set to either right or left. And in doing so, we can then build, at the least, our Turing complete circuit. And it's important to note that this can be done with only one channel worth of access. If you have only one channel worth of access, you can begin propagating a reconfiguration signal. So we might initialize this cell as a stem cell, and then pass it the information necessary for it to send a stem cell initiate signal to its neighbor, and then have it convert to a wire cell, which means that it will then just pass our signals along, and so on and so forth until we fully colonize the entirety of our circuit substrate. If any of you are familiar with fourth machines, particularly the green arrays chip, it's a relatively similar process. So the green arrays chip is a grid of 144 small fourth processors, each of which also communicates asynchronously with each other, and each of which has a small amount of memory. I believe it's something in the order of 64 kilobytes. But one of the first things you do with a green arrays chip is you have two dedicated ports which connect to external I/O, and you bit bang it until you can begin propagating pattern, so that all of your cores get mapped, and you can then address them without having to serially pass your signals from one core to another to another to another to another. So we have a similar problem or a similar phenomenon with universal cells in that if you just had a chunk of undifferentiated UC hardware and you only had your JTAG out with access to one wire, then it would be a rather long process to sequentially reprogram each and every one of the universal cells. But this also has its advantage because you only need 1.1 port of access. You only need one terminal's worth of input. And then you can just Morse code your way from a chunk of hardware that doesn't do anything to a fully functional computer. All right, so I would like to get to a bit of the formal model. And so I'll begin moving a bit, and it will also make sense because it'll cover similar information to what is presented on this screen. If we're going to simulate, that is, determine what the operation is of a universal cell, then we need to have an abstract model for it. And the abstract model for this is an abstract syntax or abstract state machine. And it's not a finite state machine because there is auxiliary logic that can be performed at each state. So in a finite state machine, you can only do basically a lookup, and then you have 1.1 symbol of input, which then determines the next state that you transfer to. There's no change in memory. This is a generalization of an abstract statement or of a finite state machine, in that you have one decision you can make, but then you could have potentially multiple manipulations of the state of state, and then you determine you follow one path of output. So to achieve a universal cell, or to simulate a universal cell, we need to know what state it's in. We need to know what type it is, whether or not it's in one of the three phases of wire, processor, or a stem. We need to know what's upstream of it, so what its neighbors are sending to it, so the A prime, the B prime, and the C prime of its neighbors. Then, because each universal cell operates on a pool-based logic, pool-based asynchrony, with each heartbeat, it samples its neighbors, it samples upstream. It sees whether or not there's any data for it. If so, it pulls it inside of itself. It inhales and eliminates that signal from its neighbor's output. In doing so, this preserves the total number of signals within the system at any point in time, because each operation we're going to assert is atomic. There are various kinds of synchronizations that can be performed to actually transfer a bit of information from upstream to downstream. But in this case, we're just going to assume it's like a cellular automaton, and the change between any one state and another is atomic. But once you have the input, then there will eventually be some output, there'll be some memory, and this is all you need, sta through mem, for your wire and processor type or phases of your universal cell. But to accomplish reconfigurability, you also need something called automail, which is where special messages that are written, and the special messages are parsed on the basis of what information is passed to the buffer. The buffer is only used during stem cell reconfiguration. And then there's also additional piece of state, the control unit, which records what terminal you should listen to, what terminal the stem cell must listen to in order to receive reconfiguration signals, and whether or not the buffer is receiving data or is flushing data. And this will become important because it's a fairly short derivation from reversible logic elements of memory to universal cells to show that while within the within the processor and wire roles, there's no change in total amount of information-bearing symbols within the system. But reconfiguration seems to be an inherently side-effectful process. If we reconfigure a cell, it isn't as if we've permuted the location of the cell with another cell that already has the configuration we so desire. It in fact has changed from being wire or processor or stem to or from stem cell to a processor or a wire cell. And because of that, we will generate either those auxiliary bits of input or those waste bits of output, which were discussed earlier, and we want to have a way of controlling them, and controlling them in homogeneous fashion. So we could have, in a reprogrammable reversible FPGA, we might have energy management only at the very input and the very output of our hardware circuit. But in a universal cell, our goal is total homogeneity. There should be no difference between any one cell and any other cell, any other location, the Computronium ideal, because if there were, then there would be a bias in terms of what way we could take control over our hardware, what way we could assert our desire for manipulation of our hardware. So we need a mechanism for controlling the amount of entropy in our system, controlling the number of information-bearing signals. And we do that by allowing each cell to be able to create or destroy one bit of entropy. Which we actually have in the pseudomath page. So, since I'm running out of time, I would like to address questions. I will show you. Okay. So I'll assert, kind of without any backing, that wire and processor, the abstract state machines for both, are pretty simple. We see that we have QP0, that's where we start, QP6, only 6 states in total. Most of the operation is first comparing to see whether or not you shouldn't do anything, that is, whether you should just go to the halting state because you can't perform any operations. And you do that if you say still have input that you're waiting on some of your downstream cells to consume for you. That's what we mean by here with a pool-based data flow. If you have output on yourself, then you block upstream collection. So you essentially get buffer pressure if the downstream isn't ready to accept your information. But this is multi-stream. It extends RLEMs, which only have one point or one port active at any one time, because you collect all of your neighbor's output when you do collect output. And it's critical that you block on collection, because if you did not block on collection with output, then you would have to begin destroying entropy in some way. There's no queue in this. It isn't like an actor model where you have an unlimited queue of possible messages which can build up. And so there's only a single slot for information to be present in both input and output. And upstream is again just neighbor's output. So the formal model in natural language for a wire and processor cell are very similar in that the wire cell asks itself, do I have output? If I do still have output, then I can't do anything. All right, I don't have output. So is there anything upstream? If there's nothing upstream, I can't do anything. If there is something upstream, excellent. So now I presumably have input, okay? And then type change. Type change meaning that if one of my inputs was a stem init signal, then this is the only thing which breaks the Boolean signaling language, is that you have 0, 1, you're empty, but then you also have a special message which is to initialize a stem cell. If you don't have that, then you'll simply process your input as the wire cell has already been defined, like an RLEM with frozen memory. And a processor is essentially exactly the same as a wire, but there can be a memory switch if you had input which did not have a type change. But the stem cell is the complicated part, or the more complicated part, because in addition to asking if it has output, in which case it must ask what is its control state. Is it still receiving information that's going to determine how it how it reconfigures itself, or is it trying to flush its buffer so that it doesn't destroy 5 bits of information, but instead only destroys the 4 bits of information, or perhaps even introduces more potential information-bearing signals into the circuit. Then it asks if its buffer is full, how does it process it? One of the things that can happen from processing the buffer is that the stem cell sends messages to itself, namely self plus message turn into a wire with memory set to right, wire set to left, processor state set to right, processor state set to left, or destroy or create a single bit of information carrying signals. If it's destroying it, then it just means that it doesn't have to flush all of its buffer to its neighbors. If it's creating a signal, then it has to know for which neighbor it's going to create the signal. And although we're doing this in a triangular UC with triangular RLEMs that have 3 inputs and 3 outputs, this is extensible to arbitrary dimensions because you can simply consider the extra dimensions to be null values, be dead, to never be used, and you'll still retain all the universality of your lower dimensional RLEMs. So that might be one of the ways of getting around the expansion in apparent size, expansion in apparent gate complexity between an RLEM without geometrically explicit circuits and a UC circuit where everything must be completely explicated. Every wire we see here must be completely explicated, and in turn requires some number of UCs set to wire phase. Yes. So, then if we look at the abstract state machine for a wire and a processor, we see output not equal to empty, don't do anything, equal to empty, continue, upstream, empty, don't do anything, not equal to empty, our upstream goes to empty because we consumed it, it's now become our input. We ask, we classify our input, does it contain a stem init signal? If it does, then there's a whole series of transitions that has to occur to become a stem cell, and this is its final state. If it's just a standard signal, then it queries the memory, sees if it's in right or left mode, and then with a wire, it just passes input to empty and output to the input rotated right or the input rotated left, and then this is our final value, our 2 potential final values for a wire cell that has fully exhausted its abstract state machine. And for a processor cell, we have the exact same sequence, with the exception that memory is swapped. The stem cell becomes a bit more complicated, but I will note that this additional complication is because we are using abstract state machines as opposed to fully expanded finite state machines. We have 25 states in total, including all of the process buffer states and all of the process automail states. But if we were to, say, expand out the queries which determine whether or not input is present at a particular input or at a particular input terminal, because our control unit doesn't actually have a control rail set yet, then this would become at least 3 comparisons, at least three states in a lookup table. I'm actually going to run out of time, so I fear that I must conclude a bit abruptly, but I will take 5 minutes of questions if anyone has them on what I've shown so far about the reversible, asynchronous, or reconfigurable facets of universal cells. Yes.
How often do you picture going into reconfiguration? Is it just like when you power on your computer, or is it like once every instruction?
Yes. So not every time you power on the computer, because you can choose persistent memory. There's no reason why you can't. Not discussed here was potential physical implementations, but there are things like you can just have a capacitor which keeps it up just like regular NAND, or you could have magnetic memory, or you could even do things like have RF circulators, which are electromagnetic computers of a sort, which have iron ferrite core magnets, which can then be charged different polarities, and then that's persistent across power up, power down. It should be the case that most of your hardware is in either wire or processor mode, and that you only reconfigure when you have need of or desire to do so. Yeah, there is no necessity to perform universal computation. There's nothing about the reconfigurability that's necessary to perform universal computation, because this circuit we see here, this GELC, the geometrically explicit logic circuit, only contains mostly wire form universal cells, and then 4 processor form universal cells. Correct. Yes. I think you went first.
So this diagram, I think, is interesting because you have a number of missing connections.
Yes. So we have this connection here, which is not drawn in, and these two here, which are not drawn in. But this right here is the only one which has been removed for the sake of actually clarity. So there is a connection between here.
So regardless, when you lay this out in a 2D configuration, you're going to have edges, right? Presumably one of them will be input and one of them will be output, but then you have 2 that aren't connected to each other. And you're going to have to dump information on the outputs coming from those edge cells. So,
Unless you have a toroidal geometry.
all right, great.
And also, so we see here we have these edges here where there's nothing, like we don't have our hydrogen atoms connected to our carbon atoms. If they are in right configuration, there won't be anything, and you don't have anything coming in through the A, or in this case the B terminal, then nothing will ever go out. So if you're aware of the edges of your hardware when you're reconfiguring your circuit, then you can just never set your RLEM to spit things out in that direction.
At that point, though, you've lost universality, right? Because those edge nodes now are different and biased to what you're saying.
You will lose homogeneity, a little bit of homogeneity. But when I say universality, that means you had to order a larger chunk of hardware, then it's just like running out of memory right now if you try to do some computation that exceeds the physical limits of your computer. Yes, ma'am.
So, if I'm understanding this correctly, if you have an infinite lattice of these cells, you want to run some program, you can visualize it as just a bunch of wires and processors in some configuration that might be sort of changing over time, these snapshots. But what I'm imagining is there a sort of equivalency that's well understood where you can have like an optimal number of cells or an optimal volume or area of cells where you can fit a program, but then you can take away cells and then just have more phase transitions of the cells in order to do the same computation and just take a performance hit from the phase transition, I guess.
Which is basically what we do now. We don't convert all of our algorithms into ASICs, application-specific integrated circuits. We instead have memory upon which our processors load words and into cache and operate on them, or into the registers, operate on them, and then return the values to memory. So you'd be able to reconstruct such higher levels of computer architecture. Or if you so desired, you could push it all the way down to, yes, lowest level. As to your question of whether or not there's an optimal balance between those two, I do not think it's a settled question. We know that for things like digital signal processing, or if you have very wide word widths, you do want to push as much as you can to the hardware level, to the native level. But if you're doing symbolic processing or dynamically sized values, then you might just want to have some generic memory space that isn't pre-allocated to a certain fixed size. Yes, and that's the last question. I have to leave. Back.
Do you have like a simulator, like a practical side to compare
Yes, so I have a simulator in Scheme, and that is on my GitHub account, and I will post all of this to the LambdaConf GitHub so that you guys can play with it. Also there's, later in this talk, there's described a miniKanren simulator, so a logic programming language simulator which lets you show that it's how trivial it is that inputs can become outputs, and vice versa, because in relational programming languages, inputs are already indistinguishable from outputs. All right, I can take your question as well.
It's just state of the universal cell is required for implementing the reconfiguration from specification from other cells.
That's correct.
Is that like necessary to preserve the reversibility, or could you increase to just broadside high internal initial configuration where we set up once from like a hardware?
Correct. So let's say you had the two-dimensional plane, then you had like a three-dimensional cross-section, and then you zapped the configuration into each of the cells. That would be very similar to what we have now with FPGAs, and that requires additional circuitry, which is not comprised of universal cells, it breaks the homogeneity.
Okay, so it's like when you describe as Morse code in the initial state, like one cell at a time from a single initial wire, that's required to preserve the reversibility.
So you should only have to Morse code it until you get parallel access, so until you define a parallel access bus, and then you can have higher throughput. And that is the last question I can take. Thank you all very much.